Hi, my name is Dennis and I'm a co-founder of creaidAI. In this video, I will demonstrate how our AI blueprint engine can be used to build a custom deep learning model, including basic data loading and pre-processing for the Titanic machine learning from disaster Kaggle challenge. For the following steps, I will use the output of our inspect data function that we mentioned earlier in our blog post. So as you can see here in this terminal window, it contains all the information I need from the training data set that allows me to build a custom model. So I'll just move this to another screen and open the workbench. So currently the workbench is empty since I haven't done anything yet. And the first thing I'm going to do is to provide some generic configuration. So in this case, I will provide a more meaningful project name. So I will name this project Titanic ML from disaster. And I will also provide the number of training examples I have. So this is optional and has no impact on the generate code, but it's a good thing to be aware of since it will have impact on the decisions made during the design process. Okay, so now we'll start building our custom model architecture. So we'll start by defining our input data sources. So I can do this up here in the left. So I just press this button here. And as you can see, a new node was introduced to the graph. So generally, operations are visualized as rectangular boxes, as here the data loading operation, and outputs are always represented as circles here. And we also provide additional information to these outputs. So here, this output from the loading operation is named source and has a dimensionality of n by 10, where n is a variable and just represents a variable amount of instances you will pass through the network later on. The name of the output will be used later in the code. Yeah, so if you choose more meaningful names, this would obviously make your code more readable later in the end. So we will go ahead and edit this node and configure it such that we can actually load our first features. So in this case, it will be the age and fair that we are loading. We also define the path where the corresponding source data file is located on our local disk. So if you feel uncomfortable putting your real data path here, this is totally fine. You can put here some dummy path. So later on, when the code is generated, we also generate a command line interface, which exposes a variable that you can set with your actual path to the data. So you can basically do this later at runtime if you don't want to do it here in the online tool. The next thing we have to specify is a source access key, which defines how the feature should be extracted from the loaded data. So in this case, it will be the third and sixth column of the data. The next thing we will take care of is the data type. So the data type of the features. So we provide various choices here, various data types. If you cannot make anything out of these names, we always provide here small tooltips that further explain what this data type, so what data corresponds to this data type that we provide here. In our case now we have numerical features, and the float vector data type is just fine here. So we have two of them. We specify that we have a CSV file from which we load the data, and then we are done. And as you can see, the output has been renamed to age of and fair, and also the dimensionality of the output has been updated to n by 2. So I will go ahead and define the other input sources. So the next one is the number of sibling and children and parents of a passenger on board the Titanic. So I will just call this like this. And again, provide the path to the data file, which is the same as before. So I'll use them more often, so I will copy it now. And in this case, the features are accessed like this. So in difference to the previous feature, now we have counts. So we will here choose a proper data type. So this is kind of important because in dependence to what the outputs of an operation have for properties, we offer different options to choose from to define the next operations applied on these outputs. So a count vector will, for example, have different preprocessing options than a float vector. And we will show this in a minute too. So here we also have two features. It's also loaded from CSV. The next feature is the gender of the passenger. And it's in the second column of the CSV file. And it is a single binary value. It's also loaded from this CSV. And the next is a ticket class. And it's a single categorical value. So for categorical values or features, we have to provide the vocabulary size. So the number of categories that are encoded by this feature. We know in this case that there are 3 categories. And last input feature is embarked, which is accessed here to the 8th column. And it's also a single categorical feature with a vocabulary size of also 3. Okay, now I've defined all the input sources I want to use in my model. And next I will define the target source, so the data we're going to predict, which will be the survival of a passenger on the Titanic. So I will just give it the name survived. It's loaded from the same CSV file. So you're not limited to just load data from a single file. So you could provide any file here if it suits your use case. Just for this data set, it just happens that everything is stored in one file. So this one is in the first column. It's a binary class, so this is fine. And we also load it from CSV. So now all the data loading has been defined. And the next step, we will define some basic data preprocessing. So we'll start with the age and fare, which were float vectors. And here have the option to set as the next operation the preprocessing type. And yeah, so here I'm offered the method to standardize the float vectors, which I'm going to use here. So it will just subtract the mean and divide by standard deviation. So as you can see, the new operation has been added to the graph. The next one, the counts, it will offer me a different method. So here, what you normally do with counts, especially if if you have large numbers, you log transform them. So we're also going to do that. And the other features we will just keep as they are. So for the categorical features, we will learn we will learn embeddings. So we will define this later in the network. So in order to start the network building, we will simply say, okay, we want to do so here. So then the next operator that's introduced here, when I press this button, is an input layer. So it's automatically defined from the outputs that are given by the previous operation. And I will just do this for all the input data. And now I have a new option that tells me, okay, set layer type. So now I can actually start building the network architecture that operates on top of the input data. So here I will, as I said before, the categorical feature, I want to learn embedding. So I will choose the embedding layer here. And for the other categorical feature too. And for me, dimensionality of 16, so the embeddings have a dimensionality of 16, seems a little bit large considering the size of the data that we have, so I will reduce this to 10. And you might have noticed this little box up here, which says model parameters. So it counts the amount of free parameters that are currently in your model, so the ones you have to optimize later on during training. So we feel this is important to watch and to monitor, since you want to keep track if you actually going to over parameterize to your model too much um, um, with respect to the amount of training data you have. So for this small data set, it wouldn't make sense to have a model that has millions of parameters. So here we can keep track of the number of parameters. So and as you can see, if I change here the embedding size, that also the number of model parameters is reduced. So in the next step, I will fuse all the different inputs I have here. So here I have an option to merge various outputs. So after I click this, I'm offered with some different, so basically the other downstream outputs that are presented here in the graphs. So here we'll select just input one and concatenate it. So I've seen already that with as you can see, the method provides here default names for the various outputs, which of course you are free to edit, and we recommend to edit them to more meaningful names. It will also make the the editing process, design process much easier, but it will also make the generated code much more readable. So here we'll just change this to something more meaningful. So I will call this input age and fair. Input and this is gender. So here we'll edit the embedding name. So we'll call it just its embedding oops. So now if I want to merge different outputs, it's much easier for me to decide which ones to pick if they have more meaningful names. So the next one I will put the input gender to concatenate. It doesn't really make a difference in this case because I'm merging everything anyway, but if your architecture gets more complex, it might be a good idea to have meaningful names here. Um, so So now I've merged all the different data sources I have. So the embeddings, the with the agent fair and other features. And now I will actually start to build a set of alternating dense and batch norm layers. So first I will start with a batch norm layer here and then a dense layer. And as you can directly see, so this dense layer here, by default, it comes with 100 hidden units. And as you can directly see here, up in the model parameters, has started to increase dramatically. So now I have already 3 times as many parameters in my model than I have actual training examples. So here I will try to reduce the number of parameters because if you over parameterize your model too much, you might your model might be prone to overfit and even might degenerate and not learn anything at all. Yeah. And something else here that's wasn't there before. So if we look at the output here, so we have some additional information. Since this dense layer, we applied a rectified linear unit activation function. We also get some additional information here in the output that tells us the range of the values that come out of this layer. So here it will be any value greater or equal to 0. And yeah, we'll go ahead and another batch norm layer. I will decrease the size again. Yeah, so here I will use now one of our auto connect features. So for predicting a target, so by choosing this option, we can select a target. So in this case, we only have one, but there might be cases where we have multiple targets to choose from. And then we'll try to basically add layers that predict this output. So we try to add a minimal amount of layers here to do this. So when I click this, there were automatically 3 layers or 3 operators added to the graph. So the first one is a dense layer that outputs an m by 1 dimensional output that is further piped through a sigmoid activation function that results in values between 0 and 1 that we need to predict the binary class here. In addition, we also have a loss node was added. And also for the loss node, I can define the name of the target variable that will be used in the code, name of the loss, and I can also choose here from a suitable loss function. So in this case, a binary cross entropy loss is selected, which is just fine for our use case. And yeah, and I forgot a batch norm layer here, but this is no problem. So between these 2 dense layers, I would like to also have a batch norm layer. So I can just here insert another operation. And something else to note here. So here I've introduced an undefined operation because I haven't decided yet what to put there. And I get directly notified that something in the graph is wrong. So here, all the upstream nodes have undefined outputs because one of the inputs is not defined. So the tool is also trying to give hints where there might be problems in the model definition. So here, I would choose now the batch norm layer, which should resolve all the present conflicts. Yes. So you might also have noticed that we have a small minimap here on the right, which gives an overview on the architecture. So for this small architecture, we don't really need it, but if your model gets really big, this minimap becomes really handy because you can use it for fast navigation and also to have a better overview of your complete model architecture. So now we have finished our design process. We will further configure the model training. So this can be done here. We can set where the model should be stored on disk. We can define the mini batch size. So to me, 128 seems a little bit large compared to the size of our training data set. We will train for at maximum of 100 epochs. We will just use the Adam step rule with default parameters. But in addition, we will also have some weight regularization. So here L2 regularization and make use of early stopping. So here 5% of the training data set will be used as a validation data set that, based on this validation data set, we will monitor the error on this data set. And if there is a consecutive, if it after consecutive steps, 10 steps, it will not increase, it will stop training. So, yeah. Okay, after so I'm now satisfied with the architecture I have right now. So now I just press the button up here and right to generate the code, and the tool will now compile the source code for this model and offer it to me for download. Yes, so I want to download it. Um, then, oops, then I will. So it's on the desktop here. Then I will select it and extract the files to my project folder, which in my case is in the temp folder. Yes, and then I can use my terminal again. So I've already pre-installed all the requirements to run the code. Um, if you know struck with that, so we probably in the README, as we mentioned in the blog, there is everything described how to set up the environment to run the code that we generated for you. And yeah, so I will just go ahead and run the training script. So first, I will show you the command line interface. So as mentioned before, there are various options that you can use to configure the model training. So one is source file. As I mentioned earlier, if you didn't feel comfortable putting your real path in the web UI tool, you can put it here later on. Um, but since we have properly entered everything into the web UI, we can just go ahead, train the model with the default parameters, and yeah, hopefully it should train. Yes, so now the model trains on the data, and yeah, that's it. So thanks for watching.